Some time back, we wrote down Euler-Lagrange equations, and last time we were looking at some of simple examples where we got to get some practice with using Euler-Lagrange equations. Okay, since we have been making Lagrangian as a central thing, let's look at some of its properties now. Okay, so properties of Euler, properties of Lagrangian. Okay. First thing is that Lagrangian is a scalar quantity. Okay, unlike when you use Newton's equations of motion, you have to know forces which are vector quantities on all the particles to find out how the system is going to evolve. But when you are using Euler-Lagrange equations, what you need to know is the Lagrangian, which is made up of the kinetic energy and potential energy, and both of these are scalar quantities. Okay, so that's one thing. Lagrangian is a scalar. Okay, so for our present context, it's scalar under rotations. Okay, also let's say you are looking at a system which has several particles, but you can group the particles into two parts. The particles belonging to part A, let's say one of the parts is called part A, those particles do not interact with the particles which belong to the part B. Okay, so I'm imagining a system with two parts, parts A and part B. There are lots of particles in there. The particles within A, they interact among themselves. Particles within B, they interact among themselves. But the particles from this group do not interact with particles from the other group. Okay, let's say that's a situation. Then can I say something about the Lagrangian of this entire system? Okay, and what I want to show is that in such a case, the Lagrangian of the entire system can be written as a sum of Lagrangians of individual parts. Okay, that's what I want to say, and it's quite easy. So what I'm trying to convey is the following. So we have a system of, let's say, n particles, and I'm saying it has two or more than two, it doesn't matter, you can take more than two also, two or more, let's say two, and two non-interacting parts. Okay, so here is your system. Okay, it's isolated from everything else. So and let's say it has lots of particles here and there. Okay, and let's say I can classify these particles into two sets. Okay, I'm not dividing a line, I'm not putting a line here to say that this is part A, this is part B, because I'm imagining the particles are all moving around, but I'm saying, okay, this guy is belonging to part A, this guy is belonging to part B, A, this guy may be part B, they don't talk to each other. Okay, so I have two non-interacting parts, A and B, by which I mean what I said. So let me represent by RA all the particles or the coordinates of the particles which are belonging to part A. So let's say R1 to Rm belong to that set, and then Rb denotes all the Cartesian coordinates of the particles which belong to set B, and I write them Rm plus 1 to Rn. So that makes a total of n if you look at both the parts. Okay, that's good. Now if I look at the system as a whole, then the Lagrangian of the system, which let me say let's call it L. Lagrangian of the system would be a function of Ra, Rb. Okay, it depends on all the coordinates of all the particles in general. That's a general statement. Ra dot, it also depends on all the velocities of each of the particles. Okay, that's what our system is. Now this, you know what form it has. It has the form of kinetic energy minus the potential energy. So I will write it as half mi Ri dot square, and I have to sum over all the particles, but I will split this sum into two parts. I will split because I can. This is an ordinary sum. So first you have sum over all the particles belonging to the class, to the part A. Then again you have half m, let me put j, it doesn't matter, you can put I as well, but I'll just put j. There's no special reason for that. And here I sum over all the particles which belong to set B. And then you have the potential energy, which depends on all the particles in the system. Okay, so in shorthand I write it like this. Okay, that's good. Now if the potential if the parts are not interacting, then the potential energy of the entire system can be written as the potential energy of the part A plus the potential energy of the part B, right? That is what it means by non-interacting. So that is what I will do. Because they are not interacting, this U can be written as U of Ra plus U of Rb. Okay, it can be split into two such parts. Maybe I should use a different symbol for U, but because it's clear from here that these are energies corresponding to parts A and part B, so I will not bother with writing the changing the symbol for U for these individual parts. Okay, now if that is the case, then this Lagrangian, as you can see, I can combine this piece with this and that piece with this. Okay, so I get L of A, that's the kinetic energy, plus potential energy of that part, plus L of B. Okay, that's one thing which we wanted to show. So this splitting can be done only if these parts are not interacting with each other. Otherwise, it makes no sense. You cannot do this. Okay. Also, let's go to next page. So I have written down two properties. Okay, property number 3. Okay, it's useful to notice that the Lagrangian which we are writing, okay, it's not unique. So it's not that if you give a system to me, there is a unique Lagrangian that I can write for it. Okay, we will come to this the reason for this also in a later video, but for now I will show that you can add a total time derivative to the Lagrangian, okay, and it will still satisfy the equations of motion. Okay, it will still satisfy the Euler-Lagrange equations. So let me write it down. So Lagrangian is not uniquely determined. Okay, which means that if I give you two Lagrangians, L and L prime, okay, they will describe the same system, meaning you will get the same Euler-Lagrange equations from them, provided the L and L prime differ by a total time derivative. So more precisely, if L prime is L plus df over dt, where f is a function of all the coordinates, generalized coordinates q's, okay, so q1, q2 and so forth, and also possibly of time. Okay, if this is the situation, then L prime and L, they describe the same system. So how do I check this? Well, what I should do is look at the df over dt term and plug into the Euler-Lagrange equation. And if the contribution arising from df over dt, this piece goes to 0, then we can conclude that indeed L prime and L satisfy the same equations of motion. Okay, they give the same equations of motion. So that's what I will do. So proof. Okay, I will not bother to give proof for a general system with several degrees of freedom. I will just give proof for 1 degree of freedom, so I have only 1 q, but you should try to repeat the proof for a system which has more than 1 q, but the proof will not be very different. It will follow the same lines which I am going to write down here. Okay, so let's look at this. D over dt, let's say I start with L, del L over del q dot. As I said, I am looking at only one coordinate now, I mean only 1 degree of freedom, q dot and t, minus del L over del q equal to 0. I am saying if I replace this L by L plus df over dt, the term coming from the f will go to 0, which means if I plug in this piece also, then in addition to this, what you have on the left hand side, you will also get the following piece. You will get d over dt del over del q dot df over dt, that's correct, no mistakes, minus del over del q and df over dt. This is what you will get extra on the left hand side. And I would like to show that this is 0. Okay, how do I do that? So let me call this term 1 minus term 2. Let's look at term 1 first. Okay, so I look at this total derivative df over dt. Okay, in the term 1 I am looking only at df over dt first. So df over dt is, remember the f is function of only q and t, not q dots. So when I take the total time derivative, I get delta f over delta t, because I have allowed for an explicit time dependence in f. Okay, so there will be this term plus delta f over delta q dot. Okay, that's correct. Now if I take a derivative with respect to q dot on this, let me take del over del q dot here over del q dot. Okay, what will that be? Now look at this piece. This piece is only a function of q and t, because taking a partial time derivative will not generate any velocity terms, right? And this piece will be only a function of q and t, this piece, del f over del q. And the time, the velocities are only in here. So when this derivative, partial derivative with respect to the generalized velocity acts on this piece, it gives 0. Here I should use a chain rule, but this piece, because it does not depend on velocity, this partial derivative is going to act only on this q dot. Okay, so I get delta f over delta q and del q dot over del q dot, which is 1. So I get del f over del q. And as I said, because maybe I should write down explicitly, delta f over delta t is not a function of q dot. Okay, it's not a function of generalized velocities. Okay, that's good. Now I should take the total time derivative. I have taken care of up to here. Now I should look at the total time derivative of this entire piece. So I take d over dt. Now I'm taking the total time derivative on the left, which means I should, okay, let me repeat it. Now I take the total time derivative d over dt, this piece, this will become a total time derivative acting on del f over del q. Okay, del f over del q. This will be your term number 1. Okay, what is that? Yeah, okay. Again I do the same thing. I write del f over del q, del over del t. So I have first del over del t acting on this piece, then I have del over del q, del f over del q times q dot. Okay, that's not a dot product, this is just a dot. Okay, perfect. Now what can I do? Okay, that's good. You see here I can interchange q and t. They are independent variables, so I can interchange them, which means I can write this as del f over del t del over del q plus del f over del q del over del q dot. Okay, if you were looking at more than 1 degrees of freedom, here your I and j will appear and you will have to take care of those things. Now this is so you have del over del q here, del over del q here. Okay, so I can write this. Sorry, I wanted to do one more thing. Okay, so you have del over del q, and then I can bring in the q dot in the bracket. I can do so because when you take a partial derivative of velocity with respect to coordinate, that's 0. Okay, so I can bring this piece in, which means I can write this as del over del q df over dt. And let's see what our second term was. Second term was del over del q del f df4 dt, which is the same here. So this is your equal to second term, which means first term minus second term equals 0, and that is what we wanted to prove, that the extra term will not give any contribution. Okay, that's another very important property that you should keep in mind, that you can always add a function to the Lagrangian which can be written as a total time derivative of another function which depends only on the generalized coordinates and time and not the velocities. Okay, that's nice. Let's see what else I can say. Next, I want to look at the kinetic energy term when we are using generalized coordinates. Okay, so you know, typically when you are using Cartesian coordinates, you have just sum over half mv squares. Okay, and when you write v squares, you are really summing over velocities of individual particles, and there is no cross term. So you do not have any term which is a product of velocity of this particle and that particle in the kinetic energy. But this situation changes when you go to generalized coordinates, and that's what we want to look at in the next video. Okay, so see you there in the next video.